Alright, we got a lot of stuff to get to today, so guys, I'm going to need your undivided attention for the majority of the class period. Where is that? Okay, so, guys, I don't really want to have to ask you again. Please be quiet right now, okay? I'm going to need your attention, like I said, almost the entire class period today, okay? Alright, does anybody have questions on this guy right now? What? Number 4? Perfect. Why is this not working? Anyways, okay. Number 4. Okay. Each time it's giving you the number. It's giving you to write the number of electrons. That's because we need to know how many we're working with each time. Okay. The only difference between number 4 and the ones above it here are we're not giving you the orbital boxes here. Okay. So. Mr. Gussie. Do you know why? So the light for the connection is like blinking up here. Do you know why that would be? Should I like unplug it and plug it in again? Or is that your best guess? It's not being very smooth right now. So we're going to have this later today. So. Huh? Okay, thank you. Yep, thank you. Okay, so number 4 is SE, correct? Blue right here. So the first thing we got to do is figure out how many electrons we have. Now, look at the periodic table. We're assuming these are all neutral, so we're going to have 34 electrons to work with here. So you'd have 34 E minus there in that blank. Now, you're not given the orbitals, but you're still going to write it in the same as you did right here, right? So the first thing that you're going to fill is the 1s. Now, if you're looking at your cheat pyramid, you can follow that right along while you do these, okay? So we start out with 1s. We got to get all the way up, literally to 34 electrons here. So always fill our up arrows first. There we go. So now our 1s is filled. Look back at our cheat pyramid. From 1s, we go to get a little more space here. We go to 2s. Okay, 2s. We go 1, 2. After 2s, the next thing that we need to fill is the 2p. Okay, so we'd write it in ourselves here. Down here, right? 2p. Fill them in. Up arrows first. They're going to repel each other, so they're going to be as far apart as possible. Okay, after we get done with 2p, next comes 3s. So make our box for a 3s. 1, 2. And we go 1, 2, 3. It's 3p. Okay, after 3p, we gotta look what comes next on our cheat pyramid. Okay, it's not the 3d is gonna come next. 4s comes after our 3p. So we're gonna have to go down here. We go to 4s. Fill in 1, 2. Okay, after 4s, now we are going to start backfilling that 3d orbital. So we write in 1, 2, 3, 4, 5. This is 3d. Okay, and we'll fill them in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, at this point, we should be at 30 electrons, right? So we still have 4 more to fill in. So we look at our cheat pyramid. After 3d, we go to 4p. Okay, so we write in the orbitals for 4p. 1, 2, 3. There's 4p. Now we have 4 electrons that we need to fill in here. We always fill our ups first, so 1, 2, 3. And then our last electron goes in the first orbital here. Is it good? Oh, okay. Okay, do we have any other questions on electron configurations? No? Yes? 8. Okay, so quantum numbers. Well, what? I don't know, I always just open them themselves. Okay, so number 8. So obviously I can't have the sheet that you guys have right now in front of me because we don't have the smartboard. So let's just go through quantum numbers. So we're just going to do one for an example up here. Okay. So how we run through quantum numbers. First things first, I'm just going to pick an electron here. So we're going to go through an example of what you would do for number 8. Okay. So I'm going to pick this guy right here. Okay. We want to know the quantum numbers for that electron. What we are going to do first is figure out what energy level that we're in. Okay. So the first number, always the energy level. So it's going to be 1 through 7 are our choices here. Okay, this one is obvious. We're looking at it, it's in the 3rd energy level, right? That's what this 3 represents. So we'd write 3 first. I'll find it in a second. That's weird. Okay. Next, we are going to do the sublevel that we were in. So the sublevels, remember, are S, P, D, or F. Okay, S is 0, P is number 1, D is 2, and F is 3. So here we're in the D sublevel, so it would be number 2. Okay, after the sublevel, we would write the box that we in, or the orbital. Okay, so it's where in that sublevel is the electron. And so we look at it here, it's in the middle one. Remember, these are numbered 0, 1, 2, minus 1, minus 2. Okay, it's the same for all of them. The middle is always 0. So if we're at P, this is 0, this is 1, this is minus 1. Okay, if we're at F, the middle one would be 0. It'd go all the way to minus 3, all the way up to positive 3. Here we're in 0, so we'd write 0 there. Okay, the last number tells us the spin on the electron. So if it's pointing up, we give it a plus. If it's pointing down, we give it a minus. This one's pointing up, so we call it plus 1/2. Questions on that?
Wait, yeah. So how much plus 1 minus? Or plus?
If it's up, if it's the one that's up, it's plus. If it's the one that's down, it's minus.
Okay.
Yeah.
Oh, yeah, I have another question.
Yes.
The other side.
Oh, the
Yeah.
Okay. Yep. Okay, so let's go back to the SE here. So I'm going to erase these. All right, we'll erase this. So we're dealing with selenium here. So we want to know, this is the orbital diagram. We want to know the electron configuration. Okay, so electron, and I'll just write config. The electron configuration is just a written representation of this picture. Okay, so it's literally showing us this. So the first thing that we'd write for electron configuration is we're in the 1s orbital, okay, and there's 2 electrons there. So we write 1s 2. Okay, next we go to the second one here. Okay, second orbital that we're in is this 2s sublevel, and there's 2 electrons in it. Okay, after the 2s we go to 2p. Okay, so we write 2p 6. Okay, after 2p6 comes 3s2. After 3s2 we go to 3p6. After 3p6, well, we can write this next. We don't have to do it. We don't have to write it out in the cheat sheet pyramid. It's fine right now. We can write 3d10. So we write 3d10. Okay. After 3d10, you can write 4s2, finally, the last step here. We're in the 4p orbital, so we write 4p. Now we don't write 6 this time because it's how many electrons are physically there. If you look, there's only 1, 2, 3 here, so we end with 4p3. Okay? Any other questions? Okay, let's get that note sheet out then. Just give me a second. I'm going to get it out with my computer. Let me get started with today's stuff. Yeah, the sheet that you picked up while you're coming in today. Okay, so here we go. You should all have the note sheet out in front of you. It looks, well, one of the parts looks like this, right? This is on the top left-hand side of your page. And it should say electromagnetic spectrum up there. So today we're talking about, like it says, electromagnetic spectrum. The electromagnetic spectrum is made up of different types of energies. Okay, so it's made up of electromagnetic radiation. That's what we're talking about. And basically, all it is different types of energy that are at different wavelengths. So, shh, please. Okay, when we describe these today, we're going to, wow. Okay, we're going to describe them in terms of their wavelengths. Okay, and it's going to be things that you've heard of before. So, we're talking about, like I said, different types of energy, and we're basically focusing on the wavelength that they have. And the wavelength that we're going to put on here is going to be in meters. Okay? The very shortest wavelengths are going to go on this left-hand side here. So we're talking about wavelengths that are 10 to the 14th times smaller than a meter. So very, 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 very small wavelengths. So literally there's tons of them, okay, in a meter. 10 to the 14th of them, to be exact, in a meter. Anything that has a very, very small wavelength, these would be called gamma rays. Okay, this would be anything from 10 to the minus 14th to 10 to the minus 12th meters in length, okay? After gamma rays comes X-rays. Okay, and X-rays are going to be 10 to the minus 12 through 10 to the minus 8 meters. All right, and this is X-rays, like you guys know what they are. So any X-ray, anytime you go to the doctor, if you break something and you get an X-ray taken, if you're at the dentist and you get a picture taken of your teeth, any of these things, this is what they're using. They're literally shooting X-rays, so it's really, really small wavelength radiation, and it's able to penetrate your skin, and it's able to take a picture of your bones. Now, they can be harmful for you. That's why they put, you know, they put that sheet or whatever. I don't even know what the heck it's made of, but you see the thing. What is it? You put like the vest on you and stuff that protects your organs and everything. Is a lead vest, right? Okay, sorry, lead vest that they put on you, that's to protect you from this radiation from getting anywhere that might be harmful to your body. Okay, the next size of radiation here is from 10 to the minus 8th to 10 to the minus 7th is UV radiation. Okay, so UV light, literally UV light that gets emitted from the sun as a wavelength from either 10 to the minus 8th to 10 to the minus 7th. The reason we've blown the next part of the spectrum up, this is going to be one that's very important for us, and it's because this is where visible light falls. So this is the only part of the electromagnetic spectrum that we can actually perceive with our eyes. Okay, so it's a very, very, very small part of the spectrum. Okay, and specifically, visible light is going to fall from between 400 nanometers and 700 nanometers. And the smallest wavelengths are going to be violet. The longest wavelengths are going to be red. And we'll actually, well, we're going to put those on there right now. Okay. Okay. So we're going to start out. We're going to put violet on here first. So the very shortest wavelengths of visible spectrum are violet. And we'll see it's going to be the opposite of Roy G. Biv. Next would be indigo. Guys, you try and find it on here. You come up here and you find indigo, and then we'll do it. Okay? Everybody's a critic. Let's do it. Okay, next is blue. I agree. You know what? Everybody get your watercolors out at home and you can make your little indigo and paint your pictures and stuff. It'll be perfect for you. Just have a blast with it. You can get exactly the perfect shade and you can just feel great about yourself. That'd be phenomenal. See, haha, Nubar, I can make it and you can't. There you go. Alright, green. Then, I don't know if that's green, Mr. Nubar. I think that's more of like a forest green. I don't know. Like that's probably not where it would fall on there. It's definitely the wrong shade. Okay, next is yellow. Okay. And then orange. That's burnt orange. Okay. And last is red. Oops. Okay, the important thing to realize here is that the smallest wavelengths are on this side. It's increasing in wavelength as we go this way. So the violets are the smallest, reds and stuff are going to be the longer wavelengths. Okay, after visible light, the next biggest type of radiation is infrared or IR radiation. Okay, this is going to be wavelengths typically between 10 to the minus 6 meters and 10 to the minus 4th meters. Okay, after IR comes microwaves. Yeah, like a microwave oven. Microwave oven uses literally microwaves to heat up your food. And then after that, anything bigger than 10 to the minus 2nd meters, these are radio waves or TV. So like literally when I talk about size of the waves, guys, we can think about down here, these gamma rays would be like waves that are like literally like this, like very small, close together. Okay, when we get to this end, these would be giant, big waves that are like this long. Okay, to help us conceptualize it a little bit. So what I want us to do is just draw an arrow pointing to the right, and that's going to be increasing wavelength. Okay, so I keep using these terms, wave, wavelength, that kind of stuff, but we need to figure out, and somehow, I mean, we've already had this probably back in middle school, but we need to go over, once again, parts of a wave and what a wavelength actually is. So on the right-hand side of your sheet, you have a line there that says parts of a wave, and on there we're going to draw a wave, and we're going to be labeling some things on it. Okay, so you already have this line, but we're going to draw a wave. It looks just like this, with 2 crests and 1 trough. Okay? So just draw that out first, please. And each spot where the wave crosses this median line here, I want you to draw dots. These dots are going to have a name. Okay, first, we're going to label the top of the wave. The top of the wave has a name, okay? It's the highest point of a wave, and that's called a crest or a peak. Okay, that's literally top, highest point of the wave. Okay, there's also a name for the bottom, the shortest part. Okay, the lowest part. This is called a trough. It's important to realize, even though, okay, my drawing doesn't really, I did not do a good job of this, but in a wave of electromagnetic radiation, guys, this height here would be equal to this height down here. Obviously, I did a pretty poor job of that up here, but they would be equal. Okay, so we have crest up on top, troughs here. These points where the wave is crossing this middle point, these are called nodes. One crest and one trough is going to be what we consider to be a wavelength. The height of the wave, or the height of the trough. So this distance here is called the amplitude. And it, generally speaking, controls what would be the intensity of a wave. So we're talking about a sound wave, it would be how loud it is. If we're talking about light, it would be how bright it is. Okay? It's the amplitude, or it also could be the volume. How much is taken up there.
Wait, I have a question.
Yes.
So the wavelength is like 3 there and not just 2.
What?
I only passed like, so I was like, I did the beginning to the second dot.
Yeah, it's not, so if you did the beginning to the second node, it would only be one crest. It's a crest and a trough together. Okay? It has to be one full crest and one full trough. That makes up one wavelength. Another way people sometimes say it's from crest to crest or trough to trough. So you literally have, half of this crest and half of this crest making up a full crest and then that full trough. If that makes sense. But either way, it's one full crest and one full trough. Okay, the thing that we're going to be focusing on the most from this is wavelength. And so we're going to just have to define that here. So somewhere down here, please write wavelength. So underneath your drawing, you're going to write wavelength. And wavelength is exactly what it sounds like. It's the length of one wave, but we just define it. It's one crest and one trough. Okay, we measure wavelength in meters. And we're going to have some equations that deal with wavelength today. When we have equations, we have a symbol that represents wavelength. That's the Greek letter lambda, and it's right here. Okay, we have one other thing to talk about. It's not really something we can label on this picture, but it's something that goes hand in hand with wavelength, and that's called frequency. Okay, what the frequency is, so let's write this down actually. Write down what frequency is. Frequency going to tell us how many waves pass a point, so number waves per second. So it's how many waves pass a point per second. So if I made this my point right here, and we said that this was waving because, or this is traveling. Obviously, waves are traveling, right? This would be taking like literally a snapshot in time of a wave. So this thing would be moving, right? Now, if we put a fixed point right here, the frequency would tell us how many of these waves pass that point in a certain amount of time. Okay? Now, there's going to be a relationship that we're going to describe between the frequency and the wavelength. Okay, so if we take a look at my small waves down here and my big waves over here. If I had a given point here, which one's going to have more waves past that point? The small waves or the big waves in the same amount of time? The small waves, right? If they're traveling at the exact same speed, the small waves are going to pass a point much more frequently than the big waves would. So their relationship has to be an inverse. So frequency is going to be high on this end and very much lower on this end. So we're going to draw an arrow that points to the left here now. Let's do it in a different color, actually. So we have an arrow that points to the left here. And this is going to be frequency. These are all increasing here. Okay, so frequency is going to increase on our chart as we move to the left. Okay, so we have some equations that we're going to use to represent frequency and wavelength and be able to determine these things. Okay, so now on your formulas, the first one I'd like you to write down is C equals, and it's wavelength. Oh, we didn't finish this, did we? I'm sorry. Let's finish frequency first. That's my fault. Let me backtrack for a second. Okay, I didn't tell you what the symbol was for frequency. That's my fault. Okay, so frequency, we got to finish this up quick. The units that we use for frequency, it's waves per second. Okay, there's a term for this called hertz. It's named for the person that coined this, that discovered this frequency. Okay, or we can write this as 1/seconds because it's something per second. So this is telling us. Or we can see this written as s to the -1, which really means just the inverse of seconds. Important. This is just a unit here, okay, and I'll show you why we use those, okay, and how it works out. The symbol that we use for frequency is the Greek letter nu, and it looks kind of like a V, you guys. So this side's kind of like flatter, and then it's rounded out to the side here. Okay, it's a symbol. And this is a symbol that we're going to use to represent frequency. So just like up here we had lambda, here we have nu for frequency. Okay, so now we can finish our equation here. Okay, so our equation, we have C equals, it's our lambda, times our frequency. Remember here, this is our wavelength. You don't have to write this down there if you already have it on your sheet, but I'm just reiterating this. This is our frequency. This is going to be a constant that you're going to add to your constant sheet. Right now, C is equal to the speed of light. And really, it's the speed of any electromagnetic radiation. So all of the things that we talked about on top. So gamma rays, X-rays. Doesn't matter how long they are, they're all going to be traveling at the same speed. That's why the frequency is different for them. Okay, the speed of light, you can add this on your constants there. So I would write C equals, and it's 3.0 times 10 to the 8th meters per second. So that's literally how fast, I mean, it's incredibly fast. That's how fast light travels in a quantified term. Or it's 3.0 times 10 to the 17th nanometers per second. The difference here, this is in nanometers, and I've already done the metric conversion for you then. Okay, so we've just converted because there's 10 to the 9th nanometers in 1 meter. That's where that's coming from. Okay, so literally those two numbers are equivalent. Okay, because C is a constant, we're not going to ask you to solve for C, right? Because we know that it's going to be the same every time. So if we know that C is the same every time, if we know either the wavelength or the frequency, we can determine the other one. So underneath your formulas, you might want to write these two. It's just a rearrangement. But the ones that we're going to be solving for are wavelength and frequency. So if we write wavelength and we rearrange this, wavelength is going to be equal to speed of light divided by frequency. So we'll write C divided by our frequency. Okay? So you write this down there by other formulas. Now these are all the same formula. It's not a different formula. We're just solving for a different variable. And our frequency then would be equal to our speed of light divided by our wavelength. So in a problem, I could say light has a frequency of whatever, whatever, whatever. You plug in for this and tell me what the wavelength is, or vice versa. I tell you the wavelength is 400 nanometers. And you could solve and tell me, okay, what's the frequency that light has? How many waves of that would pass a point in a given second? Okay, we're going to do an example with this right now. You can write this down on the back of your sheet if you would like. If not, just please follow along with me right now. Okay, so first example. It's pretty simple, but I want to know what is the wavelength of WIXX. So literally, I want to know what the wavelength is of the wave that the radio station pushes out to your car. Okay, and we know what the frequency of it is. What's the frequency of WIXX? 101.1. Okay, that's in megahertz. Okay, so remember we said the unit for frequency is hertz. This is megahertz. So we need to use a metric conversion to get back to regular hertz. Make sense? Okay, so we're at mega. To get back to hertz, we know that there's 10 to the 6th meters. Or sorry, there's 10 to the 6th in a, I don't know why I said meters. There's 10 to the 6th in a mega, okay, of our hertz here. So we're going to have 101.1 times 10 to the 6th hertz in that many megahertz. All right, now that we have our value in hertz, we need to figure out, okay, we're going to be using one of these equations. And we're going to need to use the one that solves for wavelength, right? This is a frequency. We're given a frequency, so we're asked to find the wavelength. So I want to know literally how long is that wave? Because that radio station sends out a wave that goes to your car, right? It doesn't just get transmitted through nothing. So we're actually finding out what is the length of this wave. Okay, so the length of the wave is going to be equal to the speed of light. Okay, so we're going to use 3.0 times 10 to the 8 meters per second. And we're going to divide that by the frequency that we're given, which is 101.1 times 10 to the 6th hertz. So all I do is plug in my calculator then, and I get that this equals 2.97 meters. So my wavelength, or the wavelength of that radio station, the wave that it sends out, is literally 2.97 meters long. Okay, so you're going to be given some problems that have you just manipulate this equation to solve for different variables. Okay, next, that was how we talk about electromagnetic radiation in the form of a wave. This is going to be talking about electromagnetic radiation in terms of a particle. Okay, so we probably should have heard in the past when we talk about waves or electromagnetic radiation that exists in waveform, right? We know that light exists in waveform and particle form. This is talking about particle form here. So this guy named Max Planck, he figured out that objects are going to emit energy. Now this energy is basically, when we see energy here, it's some form of electromagnetic radiation, okay? That's how the energy is being transferred. And it's transferred in the form of small packets of energy called quanta. Okay, and specifically when we talk about light, we're talking about something called a photon. And you can think about it just as like a little packet of energy that's being given off. Okay, so basically he figured out what the smallest amount of energy that something can give off. Okay, this is called Planck's constant. We need to write this down. So in our constant, we should write H equals 6.626 times 10 to the minus 34th, and that's joules times seconds. I'm not going to get too much into this number, you guys, because it's going to be very much over our heads. The more I explain it, probably the more confused you actually get. Okay, but the thing that we need to understand about this is the smallest amount of energy that something can emit. Just like there's a smallest unit called an atom, okay, there's also a smallest amount of energy that can be given off. Okay, like I said, this is literally called Planck's, and you can write this down if you want. It's called Planck's constant. So what he figured out, yes?
Does that have anything to do with length?
A length?
Long.
Yes. But we're not going to get into that right now. Okay. Mr. Blackford, are you talking more about that in your class? There you go. There you go, AP Physics 2. You're going to have to take a lot of physics if you want to get there. Okay, there you go. So, talking about Planck's constant. Now, basically what he figured out is that anything that's going to emit energy, it's going to be in some sort of number times this. Does that make sense? So it's going up by this number. All right? So that's why we have a little stair step over here. So each time we're going up, it's always in some form of this number right here. Okay? So we have a formula that's going to be able to tell us how much energy is given off by different types of electromagnetic radiation. Okay, so we're going to write down right now E equals, this is his formula for energy here. So now we're able to figure out how much energy electromagnetic radiation is giving off. And energy is going to equal Planck's constant times the frequency. So he found out that basically the energy that electromagnetic radiation gives off is directly proportional to the frequency of that radiation. Okay, so we're going to go back to our chart here. Okay, real quickly. We're going to add one more thing on here. I'm not going to erase this. We're going to add one more line pointing to the left. This is going to be energy. Okay, energy and frequency are directly proportional. So as frequency increases, energy is also going to increase. And it's always going to be something times this number. Okay? Now, E on here equals energy. H, we said, is Planck's constant. And once again, this V is frequency. All right. So, another example problem. I want to know, what is the energy of one photon of yellow light that has a wavelength of 589 nanometers. Okay, so I don't know, what's the energy of one photon of yellow light has a wavelength of 589 nanometers? First of all, if we look at this equation, all right, let's write down our energy equation first. Each time we do a problem, we should get in the habit of writing down these equations. Okay, so we know what we're working with here. We're going to have E equals Planck's constant times, okay, our frequency. Do we have wavelength anywhere in this equation? No. So can we solve for energy right now? No. Is there somewhere else in one of our equations that we have wavelength?
Yeah.
Yes. So somewhere we have frequency equals what? Speed of light divided by our wavelength here. And I'm trying to help you out because there's going to be ones like this that you have to do in your homework. So I'm showing you how to derive this other equation that you're going to be used to solve for energy too. So one, you have energy equals Planck's constant times frequency. Now, if frequency equals this and frequency is right here, what we can do is we can substitute this in for our frequency. Does that make sense, everyone? For this right here. Okay, so the last equation that you're going to write down today is literally a substituted version of this. So if you're given a wavelength and you need to solve for energy, you know that energy is going to equal Planck's constant times the speed of light divided by the wavelength. Okay, so you can write that on your formulas as well. So you basically have 4 formulas that you're going to use. You're going to have E equals H times frequency, energy equals Planck's constant times speed of light divided by a wavelength. You're going to use frequency equals speed of light divided by a wavelength, and wavelength equals speed of light divided by frequency. There's really 4 there that you need. Okay? And you'll get better at when you practice with this on your homework, and we'll have some time to answer questions tomorrow. Okay? So now all we're going to do is plug in values here. Okay? So we literally have energy equals Planck's constant. So Planck's constant is 6.626 times 10 to the minus 34, and that's joules times seconds. Okay? You're going to multiply that by the speed of light. Okay? And here we're using a speed of light in nanometers, so we can use the speed of light in nanometers per second. So we're going to write 3.0 times 10 to the 17th nanometers per second. And we're divide by 589 nanometers. It's super important. This unit here has to match this unit here. You're going to get the wrong answer. Okay. Okay, so if we do this, we are going to punch this all in our calculator. We would find out that the energy of this photon equals 3.37 times 10 to the minus 19th. And energy is always going to be in joules. Okay, so that would be our final answer here. Okay, last thing for today, you got to look on the bottom left down there on your sheet. You have a thing that says electron excitation and emission. This is real quick, okay? So on Monday, we're going to do a lab called our flame test lab. In that lab, we're actually going to be able to see evidence for electrons. So we're going to use different metallic salts. And metallic salt is just literally, it's one of our metals up there with halogen. Okay, so we're going to take sodium chloride, for example. We're going to burn sodium chloride. We're going to see what color it burns. All the salts that we're going to burn are going to burn different colors. Okay, when we're seeing in those different colors is evidence of these electron levels and like the emissions that they're going to be giving off. Okay, so when I say excitation and emission, we're going to be talking about this. So for the argument's sake here, we're going to assume that we have an electron here in energy level 1. This is what's called a ground state. It's not excited. It's the lowest energy that it can be. Okay, so this is low energy down here, high energy up here. Now, what can happen sometimes is electrons get hit with different types of electromagnetic radiation. So their energy, they're going to essentially absorb energy. Okay, so I'm going to draw a little line here. This is literally just representing one photon or one packet of energy hitting this electron. Okay, when an electron gets hit with energy, it's going to absorb that energy and it's going to make it jump in energy like this. So it's going to go from down to this ground state to the top here. Okay, when it's on top here, it's going to be what's called an excited state. when it's in an excited state, it can't stay there very long. Okay? And by not very long, I mean almost instantaneously. So it's in this excited state. All right. What's going to happen is it's going to immediately be given off this same radiation. So it's going to be directly proportional to the radiation that it took in. So it takes in energy here. It's going to emit that radiation. And in our lab on Monday, we're going to be able to see the different colors that they're emitting. Okay, so it's going to emit that in a certain type of electromagnetic radiation. We're talking about colors right now. And it's going to fall all the way back to this ground state. Okay, what we need to recognize is that sometimes an electron gets excited and it only goes to the second level here. So it can drop from second to back to the ground state. It can go from our third to our ground state. It could go from the fourth to the second. It can go from the fourth to the third. Okay, it can make a bunch of different jumps. Now we're assuming for our lab's sake that each of these jumps might be equal to different types of colors or different types of radiation. Okay, so we're actually going to get to see evidence of this radiation in class on Monday. Okay, the important thing to realize is the bigger this fall is, the more energy is given off. Okay, it's just, you can think about it literally like rungs on a ladder. Like if I fall from 10 feet on the ladder, I'm going to hit the ground a lot harder than if I fall from 2 feet on the ladder, right? There's more energy that's associated with it. So it's the same thing here. So from 4 to 1 is going to be more energy than from 4 to 3. Okay, so some of the types of problems that you might see with this are right next to it there. So the example 1 says, which photon emitted would be higher energy, A or C? So you just look at it, which one's falling farther, A or C? A. So A is going to be more energy. So you write A on here. Okay? Example 2 says comparing D and B. Which one would be green light and which one would be blue light? Okay, so why would B be blue light?
I mean, D would be blue light.
D would be blue light. Exactly. How do you know that?
Because it's longer wave. I mean, shorter wave.
No, you're wrong. I'm sorry. D would be blue light.
Yeah.
D is shorter waves. Right. So D is going to be blue light, but I want to walk everybody through this right now. So first of all, we figure out which one of these is giving off more energy. So which one's giving off more energy? D, right? So we know D is more energy. So then we go to here. We figure out, okay, what's higher energy, blue or green? Blue. Blue's higher energy. Shorter wavelength is higher energy. So blue's higher energy. So we know that D must be blue. So right, D is blue. B is green. Okay, good. Example 3, it says, what should have a higher frequency, a photon emitted by C or B? Well, what's the relationship between energy and frequency? It's the same, right? Well, they're not exactly the same, but the relationship's proportional, right? It's a proportional relationship. So all we need to do here is figure out which one's bigger, right? Which one gives off more energy? The one that gives off more energy would also have a higher frequency. So is it B or C? It's B. Okay. The back of your sheet is going to have some examples like that. The front is working with these different equations. I'm going to guess for you guys right now, the most challenging part is figuring out what equation you're using. So just you need to be looking at the variables and things that you're given in the problem. Sit tight for a second. We got a song to play for you guys. It's an electromagnetic radiation song. You really got
Better not be electric happening.